Hello everyone. Welcome to my talk on improving network architectures and training strategies for domain-adaptive semantic segmentation. I'm Lukas Hoyer. I'm from ETH Zurich in Switzerland, and I'm a third-year PhD student supervised by Dr. Dengxing Dai and Professor Luc van Gogh. So, just a brief background for everyone. What is semantic segmentation? Semantic segmentation is basically the idea that we want to get a dense understanding of images. We want to understand what is in these images. So are there pedestrians, road, and we want to do that on a pixel level. So we exactly want to know which pixel of each image belongs to which certain semantic class. The state-of-the-art approach for that are neural networks, and they are usually trained in a supervised setting. So a human annotator basically provides some ground truths to train these models. And that's one of their actually problems at some point, because you need to generate and annotate these data sets. And that comes with a huge cost. Like for this data set here, which is Cityscapes, that's actually like 90 minutes on average per image, and you need a few thousand images. So when you actually want to have your own application area, this can be a huge burden. There are different strategies to basically mitigate this problem. One of them is using synthetic data. So the nice thing about it is when you simulate your own images, your data, your simulator basically knows what it's simulating, so you get the annotations more or less for free. Then you can use the synthetic data to train your neural network on that. And it works quite well on the synthetic data, so you get nice predictions. However, when you then basically apply your network trained on the synthetic data to real data, you usually run into problems. And these problems are basically that the network experiences domain gap, things look different, and the predictions usually kind of fail. So you get a lot of noise in here, some things are not correct, some things are still correct, but still that's nothing you really want to deploy in the real world. And that's the goal of unsupervised domain adaptation. We basically want to adapt a network trained on synthetic data to the real world without any annotations. So we have the images, so we know how it looks like, but we don't know what's in these real images, but we still want to adapt the network. There are different applications for domain adaptation. The first one, the motivational one, is synthetic to real. But it can also happen that you have your data set captured, let's say, in the US, but you want to then apply your system still in Europe. So different locations, there can be a quite huge domain gap. Can be lane markings, can be traffic signs. Day to night time, when you have your daytime data set, maybe you want to still drive at dawn or even during nighttime, there's quite a considerable domain gap here as well. It's the same when you have your data set in clear weather and drive in adverse weather, like rain, snow, fog, whatever. So there are a lot of applications in autonomous driving where this actually matters. There are like two main strategies to basically do domain adaptation. One of them is adversarial training. The idea behind that is that you basically train a semantic segmentation network in a way that a separate discriminator network is not able to distinguish between source and target domain features. So you basically add in a discriminator network over here, and then you basically train it to distinguish source and target features. And the goal of the segmentation network is basically to fool the discriminator, so to align both feature spaces. The second strategy is self-training. So there the idea is that you basically have your target images, and then you train your network using pseudo-labels for these target images. And the important part is you only use the regions of the image where your pseudo-labels are confident. The pseudo-labels are usually generated by a teacher network. This can be, for example, a network that is frozen at a certain training iteration. And then basically, like after 10,000 iterations or whatever, you take the teacher network, generate pseudo-labels, then you train your student and continue in an iterative manner. But it can also be what is quite common, a momentum teacher. So you basically take the exponential moving average of the student weights and use that as your teacher. In that way, you basically generate more stable pseudo-labels and have an online update. So during the training, the teacher basically updates together with the student, but in a slower fashion. While these works on, like there's a large corpus on domain adaptation works, they mostly focus on the domain adaptation strategy. However, in our work, we look at a different aspect, which can matter quite a lot in real-world applications. applications. And these are basically secondary influence factors. This can be, for example, the network architecture. So an important question is, which network architectures are actually well suited to bridge the domain gap? Other things are training strategies, image resolution, crop size, or image masking. And this basically brings me to the outline of this talk. So I will first have a look at DAFormer, so network architectures for domain adaptation. The second one is going into the image resolution crop size, called the work HRDA. And the last one is looking into the power of masked image consistency for domain adaptation. So let's have a look at the network architectures. So previous UDA methods basically mostly used an outdated network architecture for domain adaptation benchmarks. That was DeepLab version 2 from 2017. And there have been quite a few advances in the supervised domain. However, these were not really transferred to the domain adaptation research. So that's what we actually did. We studied different network architecture components, more recent ones, to see what is actually important for a successful domain adaptation network architecture. Based on that, we designed one, and then we were having seen that basically we can enable an even higher potential when improving the training strategies for these. So basically regularizing the training. As a small spoiler, this helps a lot. So here we can see the progress of UDA over time, so date of publication on the x-axis, on the y-axis, the performance. We can see when looking into these aspects, we get a high performance improvement of 10.8% point in mean IOU, so basically the accuracy in semantic segmentation. So for that, we basically benchmarked different architecture components, and we found out there are two important things. The first one is, what really works well is a hierarchical transformer encoder, which generates more domain robust features, which is quite useful for domain adaptation. And the second aspect is a context-aware multi-level feature fusion. The idea behind that is that we basically get the feature pyramid from the encoder. And when we then want to fuse the different features, we also want to look at the context using dilated convolutions. That is important for domain adaptation because context relations in an image are usually more domain robust. So basically, generally speaking, like when you simulate your data, sidewalk is always besides road, cars are driving on road, like these kind of things are usually domain robust. And when we then compare like our architecture with DeepLab version 2, the previous one, we can see it both heavily improves UDA and Oracle performance. Not so surprising about the Oracle performance. As I said, like we were basically using more recent architectures, but the most important column over here is the relative performance. So the UDA performance divided by the supervised Oracle performance. That's basically a measurement like how well is the network actually doing to its capacity. So Oracle performance is the best you could achieve when you have all the labels, and UDA is what we actually achieved. So DeepLab version 2 achieved like 78% of its capacity, and our architecture achieved 88%. So we significantly narrowed the gap between unsupervised domain adaptation and supervised learning. However, there's one drawback with that. When you do it naively, the more powerful network architectures, such as transformers, they are more prone to overfitting to your data. And your data is, in this case, your source domain data. And this is not very good because we actually then want to transfer it to the target domain, and we don't want to overfit to the source domain. For that reason, it is important to come up with training strategies to compensate for that. One of them is rare class sampling. What we observed is that in your regular source domains, you have an imbalanced class distribution. So here we have the number of pixels for each class in the source data set. Important remark, the y-axis is scaled logarithmically, which means like this is really like for the bicycle, the last class, this is really a few pixels only compared to road. And then when we looked at the performance of these rare classes, we had an interesting observation. When you train the network with different random seeds for the data sampling, it can achieve very different performances. Sometimes it learned the bicycle quite early during training, and then the performance was very good. So this was nice. But when you had bad luck with your data sampling, then it only learned it late in the training and the final performance was not so good. And that is not very nice because you don't want to rely on your randomness in the training. In order to compensate for that, we basically added the rare class sampling, where we sample images with rare classes from the source domain more often than the ones with the common classes. So this heavily increases the number of pixels for these rare classes during our data sampling. And over different random seeds for the data sampling, this increases heavily the stability, but also the performance for these rare classes. Another observation we had regarding the training stability with more powerful networks is these networks are usually pre-trained on ImageNet. So they already have seen like how the world looks like and so their feature space is already quite well clustered. When we then basically apply this network onto our target domain, cluster our image, basically provide a t-SNE plot over that, color the points according to the classes they actually belong to, we see most of the classes or some of the classes are actually well separated. For example, here train and bus. However, when we do domain adaptation, we basically have to fine-tune the network. And for the fine-tuning, we use the source domain, which has another distribution. And the problem here is an overfitting problem. So we basically have a quite good performance of train in the beginning, but then it drops over the course of the training. In order to compensate that, we basically add in a thing class ImageNet feature distance, where we basically just regularize the training for certain classes that the ImageNet features are basically preserved in our domain adaptation strategy. And that heavily improves the performance of train. However, there's a very important point. We only do that for so-called thing classes, so basically objects in an image, in contrast to background regions, because ImageNet is only training with object classes, not with background. Like there's no ImageNet image is labeled road or sidewalk or whatever. So therefore, we constrain it only to the thing classes, and that really helps. When we then look at the ablation study, we can see like all the components we've discussed actually achieve a quite significant performance improvement, up to a point that we had this nice 10.8 mean IOU improvement. When we look at the different classes that improve, we can see that especially the ones, that had a very low performance in previous methods, like for example, train, we could achieve quite significant improvements, making domain adaptation way more usable in real-world applications. This is also reflected in some example predictions, like for example, here we can see this this tram over here, which is supposed to be a train, was misclassified as bus. DAFormer fixes this issue, the same as with confusions of truck and bus or truck and car. From that, we move on to the next work, where we basically look into the influence of training resolution and crop size. One problem with domain adaptation compared to supervised learning is that it's more GPU memory demanding. Because in domain adaptation, you have these additional networks like the teacher network or the domain discriminator for adversarial training. You basically need to incorporate images from multiple domains in your training, and you usually have additional losses like the ImageNet feature distance or other variants. This means that you have to compensate somehow for that to meet your GPU memory requirements. Previous works mostly use the protocol where they just downscale the training images. That's very easy. It works quite well. However, at some point you reach a limitation. This is basically in the background where you then have quite blurry predictions, more blurry than supervised training. So there's a gap to the supervised learning. The alternative approach would be training with high resolution image crops. There we can see, like if we have this crop over here, train with it and everything, we get quite good details. So everything at the first look looks good. However, there's a drawback. For these limited crops, you limit yourself with the context relation learning to the crop size, which means you cannot really capture context dependencies that are larger than your crop. And this results in some severe confusions. Like for example, over here, the sidewalk down there, which should be classified as road, is misclassified. And this is quite important for domain adaptation. Quantitatively, we see that in this plot. Here we basically reduce the crop size by the factor of 4. In supervised learning, this is 14% performance drop. In domain adaptation, that's almost 40%. So context relations and crop size is very important for domain adaptation. And this basically comes back to the importance of context relations and their domain insensitivity. As I said, like cars always drive on roads. Over here, the sidewalk is beside the road. You can see some pedestrian walking on the sidewalk. Like these context relations are super important for domain adaptation, and we want to preserve them. So we don't want to have a small crop size, but still we want to have a high resolution. So how we can basically combine the advantages of both. For that, we proposed a multi-resolution architecture that has a manageable GPU memory footprint. The idea is basically that you take a large, low-resolution crop to adapt the long-range context dependencies. So you basically take a large crop, then downsample it, so everything is fine there with the GPU memory, and you can learn the long-range context dependencies. In order to get the details, you take a small crop, because for details, like small crop is sufficient. You can preserve the high resolution. You basically do your predictions, you get the prediction. Now you have two predictions. So you somehow have to fuse them. Because the fusion will depend on the image, we basically have an additional attention head, which produces a scale attention, which is a weighting map between like the low and the high resolution prediction. And then we have our fused semantic prediction. We can train it. Everything is good. We can combine both advantages of this. During inference, we have to somehow combine the high resolution detail crops. This is not a problem with GPU memory, because during inference, you don't need to store the whole compute graph. So you're usually on a fine side. So you can do like, for example, overlapping sliding window approaches to basically like come up with a full prediction when reassembling these different crops. The other nice part about this overlapping sliding window is the network basically sees different context combinations, which gives like kind of a multi-view consistency learning in the training. For your low resolution, you can basically just take the image, then downscale it and so on. So that's quite easy. And then you have like the scale attention and fuse them. To look at the system like in practice, we have like two examples here. Here we can see the low resolution prediction. This is quite good for like large objects. We can see the high resolution prediction, which is not so good for large objects, but it's good for these small objects, like these small pedestrians here in the background. The scale attention has learned where to trust which prediction. So black means trust the low resolution prediction, white means trust the high resolution prediction. So our fused prediction actually combines the advantages of both. The same for this image, where we can see like these small traffic signs in the background are actually well preserved while they are lost in the low resolution prediction. This system can be combined with different UDA methods, different network architectures, and consistently improves the performance by significant margins. Interestingly, for self-training methods, the improvements are larger, which comes from the fact that we actually generate these nice multi-resolution pseudo-labels, which have a nice effect in reinforcing the learning of the system. When we then combine it with DAFormer over here, we can see that also over time, this is very nice performance improvement, where mostly small objects, like classes with small objects, such as pole, traffic light, traffic sign are improved, but also difficult classes, such as bus, train, and motorbike. This is also reflected qualitatively here in the example predictions, like these poles here, these pole groups, these traffic signs are very well preserved. You get some nice advantages with difficult objects where the semantics is not like well defined, like here, for example, this van, and also here, like with the bus. We can extend these works to other fields as well. So what we actually did in this preprint, we basically adapted them to domain generalization. In domain generalization, the difference to domain adaptation is you have no access to your target domain images, which is quite nice because when a network generalizes well to different domains, you don't have to care what your actual application is. So you can apply it like to adverse weather, you can apply it to like clear weather, US, Europe, whatever. So that's a quite nice property. And all these different components we've seen are actually well applicable to domain generalization as well. Like regularization works well, domain robust architectures are good for domain generalization as well. We can see here, when we apply it to domain generalization, we get very nice performance improvement over the state of the art. Another important aspect, the results I've shown you so far were just on one benchmark, so GTA to Cityscapes. But we can see over here, it also works from other synthetic domains like Cynthia to Cityscapes, but also other domain adaptation scenarios like day to night adaptation, so Cityscapes to dark Zurich, or clear to adverse weather like Cityscapes to AC/DC. With that, I want to continue to the third part of the presentation, which basically shows the importance of masked image consistency for context-enhanced domain adaptation. This is CVPR 23 paper, so if you want to get more information, also feel free to visit at the poster session on Wednesday, but you get a nice preview here. The motivation of masked image consistency is basically, again, context learning. So what we observed over here, even HRDA has some issues. We can see this part over here is supposed to be sidewalk according to the ground truth. So we can actually also see that it's basically the continuation of the sidewalk over here. However, the network confused it with road. I mean, you can imagine why. The texture of this sidewalk here is very similar of the road. So it's very easily to confuse. However, we as a human, or me as a human, when I looked at this image, I basically thought, why is the network not using this sidewalk here? It knows that their sidewalk, it knows that their sidewalk. So why shouldn't be their sidewalk? So somehow, if we look at that, we want to improve the context learning in this example as well. We want to utilize these spatial context relations like the curb in the foreground. And in order to push the network to utilize these context informations, we basically come up with a masked image consistency plugin for UDA. It's inspired by masked image modeling, which has been shown to be a very good technique for self-supervised pre-training, but we did a few modifications here to basically use it for domain adaptation. So the general method is you randomly mask out patches of your target image. And then you try to predict the full semantic segmentation. So we have here a pseudo-label for the target image, and we have our masked input, and then we basically train the network only using the visible patches from here to try to predict the whole semantic segmentation. And in order to do that, the network has to learn context relations, because otherwise it cannot fill in the blank masked parts of the image. As we have no ground truth, we have to resort to pseudo-labels for the target domain. We use the teacher again, like self-training style. And one very important aspect is the teacher has access to privileged information. So it can use the full target image. So it can also use the local patches to predict the pseudo-label, while the student network here has a harder time only using the masked images. However, due to the online update of the teacher over here, this learned context relations will also propagate into the teacher. So at some point of the domain adaptation process, the teacher network can use local and better context features, which again then improves the pseudo-labels in a self-reinforcing manner. If we look at the example from the previous slide, we can see this fixes our issues. And maybe here another example, just to see like how the masking actually works, what the network has learned in the course of the training. We basically, during inference, just have different variants of the same image here, which are masked. And then that's the network predicted. So over here, the network can only see the body of the rider. We can see the network without any context confuses the rider with a pedestrian. However, what is more interesting over here, if we only provide like the upper part of the image, so basically the head of the rider with the helmet, the network is able to use the context clue of the helmet to predict the entire body of the rider correctly. I mean, it's not very precise. I mean, it has no spatial information. So there's basically just like a bulb over there, but it's quite impressive. The same for the bicycle. Seeing the bicycle with the legs over here, the network has learned to basically fill in the blank and predict the rider's body from there. And then when giving the MIC trained network the entire image, we can see it utilizes the different context clues and also the spatial details, and we get a nicely predicted rider with all the segmentation details and the right class. This can be integrated into different UDA methods, into different network architectures, improves the performance by 2 min-IU on top of HRDA. So we are coming close to supervised performance. So it's really becoming better and better over time. But what's also nice is we can apply it not just to semantic segmentation, but also other wisdom charts. We can use it for image classification domain adaptation. We can use it for object detection domain adaptation. We can use it for different domain gaps, synthetic to real, day to night, clear to adverse weather, and we get consistent performance improvement from 1.5 percentage point up to 4.3 percentage points. When we look at the class-wise analysis, we can see that the classes that most improve are actually the ones that have relevant context clues. So for example, the curb for the sidewalk, posts for fences, bicycle for riders, or rails for train. Here we can see some examples. So here, similarly, so you can see the curb over there. It fills in correctly the sidewalk part over there, while HRDA struggled with that. We have a tram during nighttime, which is quite challenging, using like the parallel rails probably. I mean, I'm just guessing here. The network is able to correctly segment the train there. Similarly with the sidewalk during nighttime. And also here in object detection, the network is able to detect the rider on top of the motorcycle, while previous methods failed to do that. So concluding the talk, we have seen that secondary influence factors, so basically not the main domain adaptation methods, but like orthogonal components like network architecture, data sampling, regularization, image resolution, crop size, or mask image consistency play a huge role to make domain adaptation finally come very close to supervised learning. The source code of all these projects is available on GitHub. And if you have any questions, all my context details and these kind of links are aggregated on my personal webpage. So feel free to visit that, approach me after the talk. And with that, I hope you have maybe some free time in Vancouver and really enjoy the city. It's a nice city. You can go for nice walks and hikes in North Vancouver. This picture is taken from Kitsilano Beach, so basically the other peninsula. Explore the city, it's really cool. Okay, thank you.
Okay, so the question we have online is, my simulator doesn't generate segmentation mask. What's your experience from off-the-shelf segmentation models, and or how would you approach the UDA problem in this case?
Okay, for like off the shelf, like maybe Segment Anything might do a quite good job. When we then basically look at just using existing data sets, so off the shelf, like for example, Cityscapes, we still experience a domain gap, like when looking to other domains like Berkeley Deep Drive or Mapillary, even though it's both real world. So it's a good question. So if you don't have a synthetic source domain, which has labels, what you could do is using like another domain, like Cityscapes, for example, using that as source domain and then basically adapting to your specific application. So this actually works quite well, as we've seen like for like Cityscapes to Dark Zurich or Cityscapes to ACDC.